Alright guys, we're going to go over some definitions here. These are terms that you use to describe what you're seeing. The principles that we talked about help you decode things. The definitions are for explaining what you're actually seeing. Now the first definition is conformable. Conformable means like comfortable, conforming. In this case we're talking about rock layers that are deposited in sequence with no interruption. It means that you have three layers with no drama. No faults, no folds, no erosions, just three basic layers. For the record, in this case, these three layers would indicate that sea level is rising. Sandstone is found just into the water when you're going out into the ocean at the beach. So you find sandstone. If you walk out further, if you could weigh yourself down, walk along the water, or the ocean floor, it'd be very mucky and gooey. That's where shale is formed. If you go far enough, you get to a coral reef, or maybe just to the abyssal plain, where the only thing that can really build up are segments of microscopic sea creatures. So this right here indicates to a geologist that we're looking in an area where sea level was rising. There's no erosion, no drama. So this is conformable. Now, it's a fact that conformable and continuous layers are not found anywhere. Because that would mean that you have rock layers that are 4.6 billion years all the way up to today, all stacked up on top of each other. But our planet recycles. We have subduction, we have seafloor spreading, we have weathering, erosion, we have all kinds of drama. It's a very dynamic planet. So there's nowhere on the planet you can go and find all the layers for the history of the Earth in one place. Instead, you'll just have to jump around. They can go to Canada, and they can find some of the oldest rocks from the beginning of time. They can move further south, down to Illinois, find rocks from the Silurian. Move farther south, down to Mississippi, find rocks from the Carboniferous. And, of course, you can find rocks from today in Hawaii, where lava is just crystallizing. So conformable continuous layers are not found anywhere, but if you jump around enough, you should be able to find layers to make up or piece together the history of our planet. So conformable is, it's nice, but it's boring. And you want some drama, you're talking about unconformable. Unconformable means you have a break in the rock record. That's the fancy way to say it, but usually I just say, okay, we're talking about erosion. We're talking about erosion that comes along and disturbs. So maybe we have a situation where that same sandstone forms, but before the shale came in, there was some erosion. That shale formed, but before the limestone, there was some erosion. It's pretty much recognized. Erosion is always drawn by little wavy lines. And geologists would say that if you have erosion, it means the rocks were exposed to the surface. So deposition happens underwater. And erosion happens on land. There's a couple ways to change sea level. Obviously, you can have an ice age that locks water up in the ice on the continent, so sea level drops. You can also have plate tectonics. You can have land lifting, like we had in the case of the Japanese earthquake in 2011, and that will cause sea level to be more shallow, push more water up on land. You can have lots of new ocean floor being made. Ocean floor is warmer when it's first made, so it's actually higher rock. The rock pushes the water up. So there's different ways that sea level can rise and fall. Deposition happens underwater, erosion happens on land. So, if everything's perfect, it's conformable. If there's drama, unconformable. There are three types of unconformities. C, D, and E are the three types. The first, C, is an angular unconformity. An angular unconformity is when you've tilted or folded rocks that are overlain by younger, flat-lying strata. So in this case, we have our same three layers, but they've been tilted. and then some erosion, and now let's just put a conglomerate on top. So that's the erosion right there. Everything's angled underneath it, so we have an angular unconformity. Now you may be like, hey, how did those rocks get tilted? Probably through compression. You know, when two plates are colliding, you have mountain building, you have folding, sometimes you have faulting, you have earthquakes, but that's generally the way we get layers that are tilted up like this. This is called an angular unconformity because the erosion has layers that are angled underneath it. The next one is called a disconformity. With a disconformity, everything's horizontal. It's very difficult to distinguish, and it's also the most common. This one is tricky. So with a disconformity, you have your sandstone, and maybe that shale would have formed next, but that shale would get completely eroded away before the limestone could come in. So to you and me, it might look like there was never any shale there to begin with. If we just walked down the street and we saw this, we'd say, oh, yeah, everything's fine, it's conformable, sandstone, limestone, conglomerate, no big deal. But if we walked down the street further, we'd see these other patterns, and then we'd recognize, hey, the shale is completely missing. That tricked us. So the way I remember disconformity is that when I was in high school, if you tricked someone or made them look stupid, you were dissing them. So you'd be like, oh, she dissed you, and then you feel stupid. Well, this type of unconformity makes you feel kind of stupid because you don't always recognize it. A modern analogy may be something like, oh, you got burned, or oh, she treated your wife. So, in any case, disconformity is very tricky. Sometimes you end up feeling stupid. I will flip the page. And here we have what we're calling a nonconformity. Nothing makes me angrier than the fact that we have unconformities called nonconformities and disconformities, because they all sound the same. A nonconformity, we're not even talking about sedimentary. We're talking about either igneous or metamorphic. And basically what it is you have rock that crystallized, got eroded, and then the new rock layers form around it. You notice I'm always doing the same sequence, just to kind of explain, like, alright, these are three different options for what could happen. Erosion is right on top of this igneous rock. And they could have done metamorphic, it would have been the same story. In either case, the nonconformity is the erosion surface that's above a rock that is not sedimentary. So those are your three flavors of nonconformities. When you come across different scenarios, I'll ask you, hey, what kind of nonconformity is that? If it's igneous at the bottom, it's a nonconformity. If it's horizontal, it's a disconformity. If everything's tilted, it's an angular nonconformity. So those are your types. You'll explain what you see with those, and you use the principles to decode them. Alright, so this isn't something that you have. This is something that I just found crumpled up in my bag and decided to show you. You can see this is a sequence. It's got a lot of complicated parts, and eventually you'd be able to decode this. Right now, I can see that layers M through G are all folded. They're all wavy. According to the principle of original horizontality, they didn't start out that way. According to the principle of superposition, this one down here would be the oldest, and this one up here would be the youngest. So superposition tells us the oldest is on the bottom. Original horizontality tells me that those ones then got tilted. Cross-cutting relationships going to tell me that this fault X came later, and then this igneous intrusion right here came even later. The reason I know it came later is because it cuts across the fault. Now there's some erosion here, Y, cutting off the top of these, so those cross-cutting relationships again. Then I'm going to have a little more superposition, 11, 12, 13, 14, 15, and cross-cutting relationships tells me that the very last thing that happened here is J. Because that dike or igneous intrusion cuts through the entire sequence. So I just decoded the whole sequence using what I know, the principles, using common sense. Now, if I asked you what kind of nonconformity is Y, you'd look and you'd say, oh, well, these are at an angle. So, an angular nonconformity. That's really the only nonconformity here. This top surface was obviously eroded, but there's no new sediments on top, so we don't call that a nonconformity. So we only have one, and it's angular. So that's an example of what we're going to be doing with these skills.